So the other type of confidence interval that we're going to look at that involves quantitative data is what's known as a t-interval or a t-distribution. So a one sample z-interval is what we previously looked at, and a one sample z-interval is used when you have quantitative data and you're looking to create a confidence interval where the population standard deviation is a known quantity. So most often when we're talking about quantitative data and confidence intervals, the population standard deviation is usually an unknown quantity. And when the population standard deviation is an unknown quantity, that's when we start to talk about this whole business of what's known as a t-distribution. So a t-distribution is slightly different than a normal distribution. It has a different shape than the standard normal curve. It is symmetric with a single peak at 0. However, it has much more area in the tail ends of the graphs than, say, a normal distribution does. So if you compare these two graphs here, this is more of what a normal distribution looks like, where you have most of your data values clustered at the center with not much area in the tails, where a t-distribution doesn't have as high of a peak, and you can see here that there's more data values that are scattered about in the tail end of the graph than, say, with a normal distribution. So the other thing that comes up in this whole business of a t-distribution is what's known as the degrees of freedom. So I want to kind of sort of take you away from this, and I want to sort of pull up something a little bit different here in regards to degrees of freedom. So take a look at a question like this, and I'm going to kind of use this to explain what exactly degrees of freedom are. So this question here says, create a group of 4 numbers whose mean is 20. So if I was going to create 4 numbers that had an average of 20, so if you think of the average being 20, that would mean that the sum of the numbers, the sum of these 4 numbers would have to equal 80. So in terms of the way I could go about doing this problem, I can basically take each of these first 3 numbers and I can make them any numbers that I want. So let's just say I put a 10 here, a 30 here, and a 15 here. And I can make these 3 numbers anything I want. However, when I get to this 4th number, what I need to do is I need to stop kind of making numbers up, and I need to figure out what number do I need to put here that when I average all these numbers out would have a mean that equals 20. So I need the sum of these numbers to equal 80. So if I added these up, 10 plus 30 is 40, plus 15 would be 55. So if I put a 25 here, that would give me 4 numbers whose mean is 20. So essentially this whole business of degrees of freedom, okay, if I'm going to create 4 numbers whose mean is 20, basically I'm free to make up 3 numbers of my choosing when I go to do a problem like this. However, the 4th number that I make has to equal, in this case, a sum of 80. So the amount of numbers that are involved here, 4 numbers, I have 3 degrees of freedom, and I'm just going to abbreviate this with df, and you'll see that when we start to talk about t-distributions. But this problem has 3 degrees of freedom because I'm free to make up 3 numbers in this problem, but when I get to the 4th number, that value has to be a certain number that would essentially make this true. So if I come back to this whole thing here with a t-distribution, what you'll notice here is that when we're talking about degrees of freedom for a t-distribution, the degrees of freedom is always just simply the sample size minus 1. So the other thing that we have here is what's called a t-statistic. And a t-statistic is simply found by subtracting the sample mean by the population mean divided by the sample standard deviation over the square root of the sample size. So just some different things that are involved with questions like this. And one of the things that hopefully to kind of notice about a t-distribution is that as the sample size increases, the peak of the graph begins to increase as well. So if you take a look at this graph over here, and I'm trying to illustrate for you the comparison between the standard normal curve, which is this darker solid line here, and then here are two different t-distributions, and notice the degrees of freedom. For the first dotted line here, you would have a degrees of freedom of 2, which means the sample size is 3. So just notice that because of that, the peak is not as tall as the other graphs are, and there's more area under the tails of this graph than there would be for the others. And then if you take this sort of solid gray line that is the other graph that is on here, and this has 9 degrees of freedom, which means the sample size would be 10. And you can see here that if you compare the dotted graph to the solid gray graph, you can see the peak is higher, and then the area under the tails when you compare these would be less. So essentially what ends up happening as you increase the sample size in a t-distribution is that the graph starts to look more like the normal curve. So, and that's basically what this says down here. As the degrees of freedom increases, which is essentially saying as the sample size increase, the density curve approaches the standard normal curve even more. So we can use what's known as the inverse t on the calculator to compute the t-star score. So when we were talking about having a one sample z interval, that was when the critical value for that was the z-star score. When we're talking about a t interval, which is when the population standard deviation is not known, that is going to be the critical value. We refer to that as the t-star score. And I'll show you where this is in your calculator here in a moment. So as we kind of move through something like this here, the question here says, suppose you want to construct a 95% confidence interval for the mean of a normal population based on a simple random sample of size 12. What should the t-star score be when you do that? So to do this in your calculator, so the t-star score for this would be 2.201. So to do this in your calculator, this is essentially how you would go about that. So to construct or to find what the t-star score would be, we're going to go to your calculator. So it's on the same screen as the inverse norm. It's actually right below the inverse norm. So you would go to second vars, you would choose 4, and we're going to do the inverse t of, so once again, this formula here is the same as what we did for the inverse norm. So we would say c plus 1 minus c over 2, and then the degrees of freedom would be the sample size minus 1. So just to kind of show you what that looks like in your calculator here. So if I did this, and I went to second vars, and I go to 4, which is the inverse t. So I would put in, if I was going to do, let's say, a 95% confidence interval, I would put in 0.95 plus 1 minus 0.95 divided by 2. And let's just say I had a sample size that was 12, which we did in this case. So the degrees of freedom would be 11. So remember, degrees of freedom is always just the sample size minus 1. And that would give you what the t-star score is. So you can see that there. So it's a little bit of a different way of finding the critical value because it's a different type of different type of distribution. It's a different type of problem, but I think you can see the similarities here to what we did with the z-star score in regards to a t-star score. So if we're talking about just trying to do some different things with the calculator to compute the t-star score, so for this one here it says find the critical t-star score that you would use for a confidence interval for a population mean in each of the following situations. So if we were going to do the t-star score for a 98% confidence interval based on a sample size of 22, we would find that the t-star score for this would be 2.518, and we would get that simply from just doing the inverse t, right? So I got second vars, and I'm going to go to 4, right? So if I had a 98% confidence interval, so I would say here 0.98 plus 1 minus 0.98 would be 0.02 divided by 2. And in this case, we had a sample size that was 22, so the degrees of freedom would be 21. and that's where that value would come from for T star. So just kind of moving through some of these other ones here. So if we had a 90% confidence interval from a simple random sample of 10 observations, we would do the T inverse T of 0.9 plus 1 minus 0.9, which would be 0.1 divided by 2. And the degrees of freedom for this would be 9 since there were 10 observations. And that would be the T star score for that type of problem there. And then number 3, a 95% interval for a sample size of 7. So with this, I would do the inverse T of 0.95 plus 1 minus 0.95 would be 0.05 divided by 2. And then since the sample size is 7, the degrees of freedom for this would be 6, and that would be the T star score for something like that. So some other terminology that's similar to what we used before, and this has to do with the standard error of the sample mean, and that's simply found by just taking whatever the sample standard deviation is, and that's what SX refers to, over the square root of n. So anytime you're taking a look at something like that, that's what's known as the standard error. So the formula for a confidence interval involving a t-distribution, where once again this is when the population standard deviation is an unknown quantity. So we're going to use the sample standard deviation in place of the unknown population standard deviation, and this is the formula that you get for that right there, and that's the x bar plus or minus t star times the sample standard deviation over the square root of the sample size. So there's conditions that are involved, just like there was with a one sample z interval. There's conditions that are involved for computing a one sample t interval, and those are the same as what we talked about previously: random, normal, and independent. So the random condition, just remember that the sample must come from a simple random sample, or if we're talking about an experiment, it has to come from some sort of randomized experiment. The normal condition, remember there's two different ways to verify the normal condition. One is that if the population has a normal distribution, then you can assume that the sampling distribution is normal, or if the population distribution is not normal, meaning it's skewed left or skewed right, or it's unknown, as long as the sample size is 30 or more, we can assume that the normal condition is met. And then independence, just keep in mind that when you're sampling without replacement, which in most cases you will be, the 10% condition needs to be met in order for the confidence interval to be computed. So as far as the formula, so once again, this is a one sample, this is the name for this, this is a one sample t interval, and this is the formula that you use for that right there, which we talked about on the previous slide. So a question here says, a manufacturer of high-resolution video terminals must control the tension on the mesh of fine wires that lies behind the surface of the viewing screen. Too much tension will tear the mesh, and too little will allow wrinkles. The tension is measured by an electrical device with output readings in millivolts. Some variation is inherent in the production process. Here are the tension readings from a random sample of 20 screens from a single day's production. And the question says to construct and interpret a 90% confidence interval for the mean of all screens produced on this day. So instead of giving you what the mean and standard deviation are for this, they're giving you the actual data values that they sampled from the 20 screens that they chose. So we'll talk about, basically just run through this in sort of a four-step process type of way, and then I will show you how you can get the confidence interval for something like this on your calculator. So the state part of this, we would say that we want to estimate the true mean tension of all the video terminals produced this day at a 90% confidence level. So remember, just in the state part, you want to essentially state what it is you're estimating and at what confidence level you're going to estimate at. The plan, if the conditions are met, we can use a one sample t interval, and then we're going to check the conditions. The random condition, it said that they took a random sample of 20 screens, so that condition's met. The normal condition, a little bit of a problem here because there was no mention of the population distribution and the sample size is less than 30. So because it gave you what the data values were, one of the things that we can do is we can create graphs in your calculator to see if in fact the distribution from the samples is normal. So if you take a look particularly, here's a dot plot, which I don't know really gives you much of a view of what the graph looks like. But if you take a look at this second graph, this is the one I kind of like the most. And you can see here that the box and whisker plot, what we're looking for when we do this is, does the mean seem to separate the graph into roughly 2 equal halves, which you can see here it kind of basically does. So I'm going to assume that the distribution for this is normal. And the last graph here is a normal probability plot. And a normal probability plot, if it's linear or roughly linear, which it looks like this kind of is, that's another way to assume that the data is normal. So if you look at these graphs, it doesn't really give you any reason to suspect that it's not normal. And then the independence condition, because we're sampling without replacement, the 10% condition needs to be met. So if we're sampling 20 video terminals, we need to assume that they're producing at least 200 terminals in any given day there. So the do part of this, okay, and this is what I'm going to show you how to do on your calculator in a moment, but the sample mean for this would be 306.32 and the sample standard deviation would be 36.21. And since we're using a sample size of 20, the degrees of freedom in this case would be 19. So the t-star score, which we would do the inverse t to find, is 1.729, which gives you a confidence interval of this right here, 292.32 to 320.32. So the interpretation for this, we would say we are 90% confident that the interval from 292.32 to 320.32 captures the true mean tension in the entire batch of video terminals produced that day. So one of the things I'd like to show you with this is how to do this in your calculator. And the type of interval that we're going to compute here is a t-interval. So if you go to stat and you go to tests, I'm looking here at number 8, a t-interval. This is a one sample t-interval. And then once again, this whole business of the input where the data and the stats come in. So all the examples that we have done up to this point with quantitative data has been, it's giving you what the stats were. It gave you, instead of the data values, it summarized the important parts of the data values for you. In this case, that didn't happen. They gave us the data values. So with the input here is I want to go to data for this, because what I have are the actual data values. And what I'll show you here is that I put all of the data values for this problem in the L1 column of the calculator. So if you come back here, once again, come back to stat, test, and I'm going to go to 8 for the t-interval. So I have all the data values in L1. Each of those values occurs once. We want to compute here a 90% confidence interval. So I'm going to put a 0.9 in for the confidence level. And when I calculate this, here's what I got. So just notice with this that it not only gives you what the confidence interval is, but it will also give you what the sample mean is, and it'll also give you what the sample standard deviation is. So just something that is helpful for when you're kind of doing a question like this in sort of that 4-step process type method. So a different question here involves some different things that we've talked about with sample size. So if you recall from some things that we did with the z-interval, this right here is the formula that we used involving quantitative data for finding a sample size for a given confidence level and a given margin of error. So question here says ball bearings are manufactured by a process that results in a standard deviation in diameter of 0.025 inches. So that's the population standard deviation. What sample size should we choose if we wish to be 99% confident of knowing the diameter to within 0.01 inch? So when I go to do something like this, I'm going to take the z-star score for 99%. So I'm kind of back to z-star again because I know what the population standard deviation is in this case. So I would say the z-star score times the population standard deviation over the margin of error. I'm going to square the whole thing. And when I do that, I get a value that's roughly 41.4736. Once again, make sure you round that number up. So I would need a minimum sample size of 42 in order to have a 99% confidence interval that had a margin of error of 0.01. So this question here has some different things in it involving a t-interval again. So it says biologists studying the healing of skin wounds measured the rate at which new cells closed a cut made in the skin of an anesthetized newt. Here are the data from a random sample of 18 newts, so there's the sample size, measured in micrometers per hour. So once again, it's not summarizing the data values, it's giving what the actual data values are. So it says here that we want to estimate the mean healing rate with a 95% confidence interval. So question 1 says to define the parameter of interest, which is a part of what the state part is in the state plan do conclude. So what we're looking to find as the parameter of interest would be the population mean healing rate of these newts. So question 2, what inference method will be used? Check that the conditions for using this procedure are met. So once again, this speaks to the plan part of state plan do conclude. So because the population standard deviation is unknown, we're going to do a one sample t interval. And then here are the conditions. The random condition, it says that the newts were randomly chosen. The normal condition, we don't know if the data comes from a normal population, and the sample size was only 18. So once again, I have to take a look at what the graph of these values might look like. So I might create a histogram, or I might create a box and whisker plot or a normal probability plot to check that, which we'll take a look at here in a moment. And then the independence condition, if we're sampling 18 newts, we need to assume that there's 180 newts in the population. So if you come back to your calculator again with this, okay, so I put these data values in L2 if you notice here. So what I'm going to do first is I'm going to go to the stat plot screen, and I'm going to put this with a normal probability plot, and I want to see if this gets me a graph that's roughly linear when I do this. So if I do this and I do a zoom stat, and I take a look at the graph here. So once again, what I'm looking for is, do I get a graph that gives me a normal probability plot that's roughly linear? So if you take a look at this graph, you can kind of see here, you get a plot that appears to be fairly linear.